Well, we're about to dive into the Titanic and do penalized elastic net logistic regression. And I'm a bit puzzled because I intended you to do this and somehow I got carried away and I did it myself. It took ages. And it also means I'm now not quite sure what assignment I'm going to give you for the end of week 4. But never mind, here we go. And amazingly, there are actually no to-dos for you in this workbook, so I must have been feeling in a good mood when I did this. I've linked a booklet here, besides the maths and information about solvers in it, which you may not particularly be interested in. The rest of it is a good and useful read, and it also goes over some of the stuff we discussed in the video lectures from a slightly different angle, so that would be a good read for you. Sometimes a little bit of a pain to find out exactly what parameters the various classes have, or what arguments the various classes have, and just typing help like that can be a good way to quickly see what the arguments are and get some examples. We're going to be using the generalized linear estimator, which you've already seen. We're also going to be using grid search, and we're going to be using lambda search rather than programming the grid search ourselves as we did last time. We're going to use H2O's inbuilt functionality, and getting used to that is going to be very important for you when we come to gradient boosting and random forests. Put the data in. Do we need to impute values at all when we are using the H2O generalized linear regression model? I don't think we do. I just spent a little bit of time coding this up because some of the documentation seemed to say that if values were missing, they would just be missed out. But having read the whole booklet and gotten right all the way to the end where it talks about how it deals with missing values, it seems to me that the default is that it will mean impute missing numerics, just as we've done manually here. But now that I've done it, I might as well stick to it. Over here, for example, I'm finding out which values of age are NA, and then what I'm doing here is finding which index of my data set those missing values are at. You've seen this code before, more or less. I am being a little bit careful here to find the mean value only over the train data set, because in real life that's what would happen. You wouldn't have the test data set. And then if there are any missings on the test data set, which there are for age, they will get the mean missing value from the train dataset. I think there were 2 fares missing. It's not really important. Cabin is missing a lot of the time, but we're not using cabin. Embarked is missing, but that is a categorical, and I think H2O is okay with categorical missings. Penalized logistic regression in H2O. I did spend quite a bit of time reading through the booklet and extracting some of the more important things, and also figuring out which pages would be good for you to read. So I would recommend you read what I've suggested. Some of the things they say: don't bother one-hot encoding, especially if you're in Python and you're used to it for other frameworks. For other frameworks, they almost certainly mean sklearn, where you have to one-hot code everything yourself. They do it for you in H2O, and they do it exceedingly efficiently because one-hot encodings are always sparse, and they take advantage of that. Till now, we have searched for lambda ourselves. We almost had to do that in sklearn because there wasn't any proper way that sklearn did it for you. In H2O, they do it for you, and they do it exceedingly efficiently with something called warm starts. So it doesn't make any sense to search the lambdas ourselves, but we do need to search for the alphas. K-fold cross-validation is a little bit of a pain in sklearn. You have to use a separate class. Here, all you need to do is set n-folds greater than 1, and for some random reason I've used 20 folds in the code below. They tell you that when you're searching for alpha, you don't need to bother searching too many values. I'm actually going to search 100 values here because the dataset is small and it helps us to illustrate how the grid search works. And here's a bit about missing values. Please read that. I've just realized I'm doing this on my local machine. I am not going to stop this recording now and start up my virtual machine and do it. I hope this works. From memory, the virtual machine would be fine with this as well. It will just go straight to your local host. I am therefore using a much more recent version than you are using. If it doesn't work on your machines, it's going to be all my fault. I really hope it does work on your machines and that there are no arguments which have been introduced into this recent version that are not available for you. We just upload the data and we give it the handles H2ODF train, H2ODF test. Over here, we're choosing which values of alpha the grid search will search over. You certainly don't need more than the 4 or 5 values that we have over here. Ridge regression, lasso, and a few values in between. But what I'm going to do here instead, just to illustrate grid search a bit more clearly, is to create 100 values for the alpha. If you have a lot of models, which we do now, and if each model were to take a lot of time, which here they don't, but in your final project they probably will, how are you going to search over all of them? You're just going to run out of time. And we did talk about random grid search in one of the video snippets, and that's what we're going to do here. The strategy is random. It will only choose a maximum of 30 models to look at, but it will choose those at random, and there is a good chance that it's going to find a reasonably optimal model. Don't forget, if I do forget to mention, the other thing you can do is stop your machine, change the type of machine you're using so that it's got more cores and probably a little bit more RAM, and then H2O can take advantage of the fact that you're using a few cores to run the grid search on separate cores at the same time. So here we set the criteria for the grid search. Notice the seed. I want to get exactly the same results each time so that you see the same results that I see. You want to get exactly the same results each time so you get more than 0 marks in your final assignment. So it's always a good idea to run your code twice and make sure you get the same results. If you don't get the same results, find out where you didn't set the seed. Once we've set the criteria, we define the grid which we're going to train. It starts off with grid search, and then inside there we first say which model we're going to train inside of our grid. Family equals binomial, it'll automatically choose the logit link function. Nfolds equals 20, don't ask me why. Lambda search equals true, as we've discussed. The hyperparameters that the grid will search over are these 100 alphas. I'm giving the grid an ID. Again, don't ask me why. And the search criteria are the search criteria. Here we go. We're going to run it over the train frame. There is no validation frame, but because we've told it there's 20 folds, it will do 20-fold cross-validation on the training frame itself. On my machine here, which has how many cores? I'm not sure, to be honest. That took about 30 seconds. Now I reckon there should only be 30 models in this grid. Well, we're going to get the grid. We're going to sort it by accuracy decreasing, so the best accuracy is first. I'm actually a little puzzled about these accuracy metrics that I'm seeing over here. In some of the help that I read, it said that so long as you use cross-validation, you will get the average cross-validation accuracy. What is peculiar is that when I submit these models or predictions based on these models to Kaggle, I'm not getting accuracy anywhere near 0.81. It's at its best something like 0.77. I therefore thought that maybe somehow I was getting train accuracy over here. That's the puzzle. Let's extract the best model from the grid. I think I finished half a comment before saying that there were more models here than I expected. And when I was doing runs previously, there were more models. Although I had told it to run only 30 models, there were something like 80 models down here. But now, for some bizarre reason, it's behaving itself, and it's only giving me 30 models. Anyway, print the model. Do. That's a bit messy. It gives you a load of stuff about the model. Binomial logit. This best model, it tells you what the alpha was and what the lambda was. 10 active predictors. That's probably quite a lot for this data set, given that it only had a small number of independent variables. Gives you all the performance metrics. I hope that when you come across performance metrics that you don't understand, you should at least understand what a performance metric is in general, and you should then be able to look that up in Wikipedia or whatever to see exactly what that specific one is. Probably the most important one that we haven't discussed is something called AUC. That's the area under the ROC curve. You can view performance metrics like this. This is your model, BST. Just dot whatever the performance metric that we want. MSE, log loss. We talked about log loss. I hope you remember it. Accuracy. You can get it for train and for validation. Well, there isn't a validation data set, so it's not surprising you don't get it on the validation here. And this one is quite interesting. It's actually returned 2 values for the accuracy. I wonder if it's separately trying to find optimal thresholds for the class not survived and the class survived. One of the things the booklet says that to check your models, make sure that the validation accuracy on the 20 folds is somewhat consistent. And it tells you to do that. This is the validation accuracy over the 20 folds. You can see that most of the time it is consistent. What are the coefficients of our model? The normalized coefficients, or to be precise, the coefficients fitted to the normalized features are these ones. And as we've discussed previously, given that the features are normalized to all lie in the same kind of range, whatever is large here is in some ways an important feature. You can see that passenger class is an important feature. It's negative. Passenger class was 1, 2, or 3, and I put it in here as a number rather than as a categorical or factor variable. And sadly, that means that people in the lower classes were much less likely to survive, and this is the most important factor in the model. Over here, age is large and negative, so older people, again, sadly, were much less likely to survive. But let's get the coefficients for the original variables before standardization. You can incidentally see that the coefficient for age before standardization is very small, although it was one of the most important variables, obviously, when it was standardized. And that's going to be because age can be very large, so it's on a different scale, a larger scale, than the other non-standardized variables. I'd like to try one prediction by hand, so I'm going to look at the first passenger, Mr. Owen Harris. Unfortunately, he did not survive, but you have the passenger class, the sex, the age, and all the things we need. So what I have done over here is I've got from the coefficients dictionary the various values relevant to him, and where there are a number, and where necessary, I've multiplied the coefficient by the value of the variable itself. If I do all that, I still only get the linear predictor. I still need to apply the logistic function to the linear predictor, which, if you remember from the lectures, is e to the eta over 1 plus e to the eta. We therefore get our prediction of 0.0998. We can now predict the model on the full train and test data and turn it into a data frame. If I didn't turn it into a data frame, I would get something like this, which looks like a data frame, but is simply some information returned from H2O, and you can see it's actually an H2O frame. Some information about that frame is being returned to us. So that's not massively helpful. I prefer to have it as a data frame, and now I can just treat it as I would any other pandas data frame. Did we get the first prediction right? Yes, we did. So the prediction over here is 0.099846, and we had 0.099846. When you are fitting generalized linear models of some kind, it's pretty useful to check for yourself you can get at least one prediction right and make sure that you really understand it. After all this, do the predictions lie between 0 and 1? Well, they better had, otherwise all this was a waste of time. Yes, they do. The linear predictor, though, obviously doesn't lie between 0 and 1, and we can see here it lies between -4 and +4. Finally, let's find an optimal threshold, 0.61. Up here, if I can find it, they gave you predictions. Well, which threshold did they use? You can find that in their booklet somewhere. It's based on a metric called F1, which would be a good idea for you to look up. Predict predictions. We could submit those to Kaggle. I haven't. I've submitted various runs to Kaggle, and I tend to get something between 0.74 and 0.77. There are some kernels that people have submitted to Kaggle for logistic regression, and at least the basic kernels, which this would be similar to, are also given results for logistic regression in that kind of range. So I think we're okay. That is it. This workbook took me hours and hours and hours to create. I really hope you appreciate the fact that you didn't have to do it yourself for an assignment, but I will try to find you something else.